This video will be a complete review of everything that's in Murru's Chapter 12 on oxidation and reduction. Oxidation is an increase in CZ bonds or a decrease in CH bonds. The hydrogen carries electrons, so it can also be described as a loss of electrons. Reduction is a decrease in CZ bonds or an increase in CH bonds. It's gaining more hydrogen and more electrons. This makes sense because it's called reduction, and when an atom gains electrons, its charge is reduced. As you move from left to right, the number of hydrogen bonds are decreasing. You could also say that as you move from left to right, you're losing 2 electrons. This is oxidation. As you go to the left, more hydrogens are being added. You can also say more electrons are being added. This is reduction. There are 3 possible products that you can get based on how you add the hydrogen. You can convert an alkene or alkyne to an alkane. You can convert an alkyne to a cis-alkene, or you can convert an alkyne to a transalkene. Before we get into catalytic hydrogenation, you should know that absorption isn't the same as adsorption. Adsorption is a process by which atoms or molecules adhere to the surface of a solid material. Hydrogen is usually found in its diatomic form since it's the most stable that way. This reaction only happens with a metal catalyst, usually palladium, platinum, or nickel. This reaction adds in a syn manner and it prefers less substitution. Even though hydrogen is usually found in its diatomic form, it can adsorb onto the surface of the metal. This either partially or completely breaks the bonds between the hydrogens. When an alkene gets near the metal, it complexes with it. The 2 hydrogens are added sequentially or one at a time. Once both are added, there is no longer a pi bond to keep the alkene, now alkane, complex with the metal, so it is released from the surface. Now that you know how this mechanism works, the hydrogens are added in a syn fashion because the metal and the alkene are both in the same plane. Imagine putting a piece of paper on a desk. Only one side of the paper will be in contact with it. If 2 alkenes reduce to the same product, you can find out which one is more stable by seeing which one has a lower heat of hydrogenation. You can have enantiomers, but you have to have at least one stereocenter. Aldehydes reduce to primary alcohols, while ketones reduce to secondary ones. Another thing to note is that this reaction does not usually work on aromatic compounds because they're so stable. You need very high pressure and temperature to be able to break it. An easy way to draw the products for this reaction is to draw a line straight through the double bond. I'm going to keep everything the same on top of this line, and then choose what direction I want to add the hydrogens. If you choose to add them in the front, it's going to push the other substituents to the back. But if you chose to add the hydrogens in the back, it's going to push the other substituents to the front. This is a pair of enantiomers. You can also reduce an alkyne to a cis-alkene by switching up the catalyst. You would have to use a poisoned catalyst to only add the hydrogens onto one side. Lindlar's catalyst isn't as reactive as the other ones, so it will only add 1 mole of H2 instead of 2. This will give you a molecule that looks something like this, to give you a cis-alkene. Before we get into dissolving metal reactions, you should know that it adds hydrogen in an anti-fashion and it gives us a transalkene. We use dissolved group 1 metals like sodium dissolved in ammonium. It has a radical intermediate that forces a trans product. Here's how the mechanism works. This sodium is very unhappy because it only has 1 unpaired valence electron, so it gives it away to the carbon atom. We're using a single-sided arrow to show that only one electron is moving. The electron that's now on the carbon doesn't want to be by itself, so one electron from the pi bond goes over to it. This other one that's left over goes to the other carbon to give us this product. From here, there are two options. The cis option looks like this, with the R's on the same side and the lone pairs over here, and the trans option, which has the R's on opposite sides and the lone pairs over here. Because of valence shell electron theory, the cis one is not possible because the electrons are too close, so they're very unhappy. This gives us a radical intermediate. Remember that this reaction is taking place in ammonium, a polar product solvent. So that means the nitrogen is going to be partially negative, while these hydrogens are going to be partially positive. This hydrogen is going to attract the lone pairs of this carbon over here, and then this bond will collapse back onto the nitrogen. Remember that this reaction is taking place in liquid ammonium, so that means that there are still excess sodium molecules floating around in solution. So to take care of this radical over here, another sodium is going to come and give one of its electrons to it. So we now have a lone pair over here instead of just one electron, give it a negative charge, and a hydrogen bond over here. This carbon with the two lone pairs is still unhappy, but remember that there is still excess ammonium, so another molecule of ammonium is going to come in and give one of its hydrogens over to this carbon. This gives us our final product of a neutral alkene that has the hydrogens added onto opposite sides. We looked at three ways that you can reduce an alkyne. The first two ways are catalytic hydrogenation. The first way adds two equivalents of hydrogen gas with the help of a metal catalyst. This takes it down all the way to an alkane, giving you a product that looks like this. The second way uses a poison catalyst. This will only add one equivalent of hydrogen. Because it only adds one equivalent of hydrogen gas, it gives you an alkene instead of an alkane. This method adds it in the syn fashion to give you a cis alkene. The third way we can reduce an alkane was through dissolving metal reduction. Here we use a group 1 metal like sodium or lithium with a solvent like ammonium. This still only adds one equivalent of H2, ammonia being the source of the H2, but it adds it in a trans fashion. This is because there is an unstable radical intermediate. This gives you an alkene that looks like this. Before we get into hydride reduction, you should know that this is an SN2 reaction that prefers unhindered carbons. The nucleophile in this situation is actually the hydrogen. NaBH4 is weaker and can only reduce ketones and aldehydes, not carboxylic acid, while Stop trying to say shit. Here's how the mechanism works. For ketones and aldehydes, this hydrogen over here will attack this carbon. This will make the double bond over here go up to this oxygen to give us a product that looks like this. Keep in mind that these negative oxygens are stabilized by the sodium that's in the solution. From here, you can either quench your solution with an acid like H3O, or just use normal water. This oxygen is going to take this hydrogen over here to give you this product. Keep in mind that ketones reduce to second-degree alcohols, while aldehydes reduce to primary alcohols. The mechanism for carboxylic acid is very similar. This hydrogen over here is going to attack the same carbon, and the bond over here is going up to the oxygen. Unlike with the other two, before lithium can come in and stabilize this oxygen atom, these electrons resonate down here, which kicks out this. Now another molecule of this aluminum compound is needed to oxidize it again. Basically the same thing happens. This hydrogen will attack this carbon over here, and some electrons from over here will go to this oxygen, which gives you this product. Just like before, you can either quench your solution with acid, or you can use regular water. This oxygen over here is going to come and take a hydrogen to give you this product, which is your final product, a primary alcohol. Remember that ketones give secondary alcohols, and aldehyde and carboxylic acids give primary alcohols. If all those mechanisms were a little overwhelming, here is a simpler, more generalized version. Just like before, this hydrogen goes and attacks this carbon over here, which kicks out the leaving group. This is going to give you a product that looks like this, with the leaving group replaced with an H. You'll also have the lithium, which bonds to the leaving group, and your leftover aluminum compound. What if you have an epoxide? This reaction is going to proceed in basically the same way. This hydrogen over here is going to come and attack this carbon. This is going to kick these electrons over here to this oxygen to give you this product. It's important to keep track of the number of carbons so that you don't add in any molecules that aren't actually there. Here you can see there are 2 carbons in this epoxide, and that there is the same number over here. This is where you add your acid or water. This oxygen is going to go over and grab one of these hydrogens to give you this product. And this is going to be your final end result. Congratulations, you have officially made it to the end of the reduction portion of Chapter 12. Now that we're moving on to some oxidation reactions, we should look at some common oxidizing agents. There are 2 categories. The first ones contain oxygen-oxygen bonds. These include molecules like O2, O3, also known as ozone, H2O2, CH3COOH, and peroxy acids, which have the general formula RCO3H. The second category are the ones that have metal oxygen bonds. These usually contain some kind of chromium or manganese. Chromium oxidants include CrO3, Na2, Cr2O7, and K2Cr2O7. PCC is one that's also here, but it's more selected than the rest. One of the most common ones you're going to see with manganese is KMnO4. Some other miscellaneous ones include OSO4 and Ag2O. Before we get into epoxidation, you should know that the most common oxidants used here are MCPBA, peroxyacetic acid, and MMPP. Epoxidation is going to add an oxygen atom to an alkene to make it an epoxide. This will add in a syn manner, and it is stereospecific, meaning that if you start out with a cis reactant, you're going to yield a cis product, and vice versa. The mechanism looks something like this. First, the carbonyl is going to attack this proton. Next, we are going to attack one of the carbons of the alkene to make the first CO bond. You have to choose the least substituted carbon. In this case, both are the same, so it doesn't matter which one we choose. So this over here is going to attack this carbon. Next, the alkene is going to attack the oxygen to make this second CO bond. This will cause this bond over here to break off, giving you this product. Remember that this is a stereospecific reaction, so it's important to pay attention to the stereochemistry of the original reactants. If you have this cis alkene, it will make you draw the end product like this. But if you have a trans alkene, you'll have to draw the product like this. Here are some more practice problems for epoxidation. For this top one, we can put an oxidant like MCPBA. This is going to give us an achiral mesocompound that looks like this. For the second one, we can add an oxidizing agent like CH3COOOH. This is going to give us a product that looks like this. There are actually two enantiomers that you can get from this, so the correct answer would be this. For the last one, we can add an oxidizing agent like MMPP. This is actually going to give us a pair of diastomers that look like this. Before we get into dihydroxylation, you should know that we're going to be adding two hydroxy groups to a double bond to form a 1,2-diol, also known as a glycol. We can add in an anti or a syn manner depending on which reagent we choose. Anti does need two steps, an epoxidation followed by a ring opening. For an anti addition, we're going to be using this example. The first step is going to be an epoxidation, which will give us a product that looks like this. I'm going to label this carbon over here A, and this one down here B. Now there are two possible products that we could get based on which carbon we attack. If we attack carbon A, it's going to give us a product that looks like this, with the OH staying on the carbon A and the other oxygen going down to carbon B. Now we're going to quench this with either acid or water to give us a product that looks like this. If we had chosen to attack carbon B, our first product would look like this. This time, the alcohol group stayed back on the B carbon while the other oxygen went to the A carbon. Next, we are going to do the same thing we did in the step above and quench it. This gives us a product that looks like this. These two are actually enantiomers. For a syn addition, you have to treat the alkene with either KMNO4 or OSO4. All the oxygen atoms have to be added from the same side because it comes from the same molecule. For the one that has MN in it, it would look like this, and the other one would look like this. They can't add on separate sides because the molecule can't contort in that way. Before we get into ozonolysis, you should know that it has a very unstable intermediate called a malonoside that converts to another unstable intermediate called an ozonide. We're going to be breaking both the sigma and pi bonds to make two separate molecules from one single one. A tertiary carbon is going to give you a ketone, while a secondary one is going to give an aldehyde or a carboxylic acid. An internal alkyne will give 2 carboxylic acids, while a terminal one will give you a carboxylic acid and CO2. For me, the mechanism was incomprehensible, so let's just skip to how to draw the products. The easiest way to do this is to draw a line directly through the double bond. Then, draw the molecule exactly the same as it was, just with the break. Now add an oxygen to where the carbons used to be connected to. This will also work for compounds with rings. You do the same thing, just draw it with the break and add an oxygen where the carbons used to be connected. Here is a pretty tricky one. You can do the same exact thing. If you want to redraw this in a more linear form, I recommend numbering the carbon chain just so you don't get lost and add any extra atoms. Now you can use those numbers as a guide to help add in the substituents. So this double bond with oxygen is going to be right here on the first one. This group over here will be added on the third carbon. This one over here will be added on the fourth. And then the last double bonded oxygen will be added over here on the sixth carbon. Remember that when you split an internal alkyne, you're going to get 2 carboxylic acid groups. But when you split a terminal alkyne, you're going to get a carboxylic acid group and CO2. Before we get into the oxidation of alcohols, you should know that this reaction is usually done with chromium oxidants. CrO3, Na2Cr2O7, and K2Cr2O7 are strong, non-selective oxidants used in aqueous acid solutions like H2SO4 and water. You can also use PCC, which is a more selective or milder oxidant. Alcohols can be oxidized into a few carbonyl compounds. Primary alcohols will give you aldehydes if you use PCC, the more mild one, or carboxylic acids if you choose stronger agents. Secondary alcohols can only give you ketones, and tertiary alcohols can't be oxidized at all because there's no H on the carbon with the alcohol group. The product of alcohol oxidation is pretty easy to get. First, find the carbon that has the OH group on it, which is this one. Then take 1 hydrogen from that carbon and 1 from the oxygen. This will give you a product that looks like this, which is an aldehyde. You would get this product if you used a mild oxidant like PCC, but what if you wanted to use a stronger oxidant? You just do another round of oxidation to get your product, which is the carboxylic acid. But what if you have a secondary alcohol? The process is pretty much the same. Find the carbon with the OH group, then take 1 hydrogen from there and 1 from the OH group to give you your product, which is going to be a ketone. A few things you should know before we get into sharpless epoxidation is that it's enantioselective, meaning that it is going to make one specific enantiomer. We're going to be making an epoxide. You can control the product based on what kind of DET you use. There are 3 different components: CH3, 3COOH, a titanium catalyst, and a DET. Positive DET adds from below, and negative DET adds from above. Here are some ways that you can draw the products of a sharpless epoxidation. This first way, you can imagine a an epoxide ring coming up from there. This is going to push these substituents to the front and these to the back. The way that I prefer to do it, you just keep everything the same. The only thing you change is adding the ring. For this problem, we're going to need it coming towards us. Both answers are correct. You can choose whichever method you find easiest. Here's a pretty simple practice problem. The first thing that I would do is turn this molecule over so that's a little easier to work with. Imagine this ring is coming up from this double bond right here, and that's going to give us our product that looks like this. Congratulations, you have officially made it to the end of Chapter 12, Oxidation and Reduction.